This is lesson 1 for chapter 18. Direct current as opposed to alternating current. Direct current, the kind of current that only goes in one direction, as opposed to alternating current that oscillates or goes back and forth like a sine wave 60 times a second, at least in the United States. That's a later chapter. Direct current circuits almost invariably involve a battery of some type. If you look at this opening paragraph, you'll notice some rather interesting words being used. First of all, the word control. And one of the purposes of science is to enable us, scientists, but people in general, to control certain circumstances. When you see that word control, there's an aspect of dominion, of ruling over, that comes straight out of Genesis chapter 1. And remember, this control or dominion is always in the context of stewardship and glorifying God as the reason for why you are going to control or have dominion over this very, very small piece of creation and natural phenomenon. The other word that's kind of interesting here leads us to the concept of redemption. Science, for example, among a million things, it can increase farming productivity or just increase productivity in general through assembly lines and robotics and things like that. Increasing productivity is a way in which to do more with less energy, maybe with less number of people having to do routine, boring, repetitious, or dangerous kind of work. It also, for example, in the area of medicine, allows us to save more and more lives, allows us to enable people to live longer and longer, but not feebly, but longer and longer in the terms of being able to be productive into their 70s and their 80s and later, and at least to be able to continue to have meaningful relationships. And so right now, there are hundreds of thousands, if not millions of people around the world that are actually over 100 years old. But all of this is an example in terms of saving lives and increasing productivity, increasing the amount of food that's available, making life more comfortable and bearable, reducing the number of people in poverty. All of this is a good example of God's gift of science that enables us to participate in his redemption. Obviously, of course, science alone cannot redeem anybody or anything. But God gives us glimpses of redemption and allows us to play a small role in enabling other people to be fruitful and multiply and fill the earth. That was a free Devo from yours truly. Now, where does this direct current come from? How can we maintain electricity going in one direction through a circuit? And the answer to that is with a battery. Remember, in chemistry, we would call this an example of an electrochemical cell called a voltaic cell, or an old-fashioned example would be a galvanic cell. And this is the result of chemistry. If you have two different kinds of metals, usually, and some electrolyte kind of material between those metals, you automatically have a battery, a device that can push a current through a wire. Now, the old-fashioned name for this was EMF. And this EMF stood for electromotive force, which it tells you at the bottom of the page. Excuse me. Now, the main reason we don't use these words anymore, of course, it's not a force, not at all. I almost think what is a better definition of EMF is it's an oomph, a way of pushing or pumping a charge through a wire. It goes through the wire. It does whatever work it needs to do. It comes back to the negative end of your battery, plumb tuckered out with zero energy. And then the battery, through chemistry, gives it energy back again. It charges it back up so it can go around and around and around the circuit, hundreds, thousands, millions, billions of time, until the battery eventually wears out, like all things eventually do. Sometimes you can recharge the battery and use it again, and sometimes the battery has to be thrown away or hopefully recycled. So an EMF is not a force. It is a source of energy per charge, or the ability to do work per charge, and that is called a volt. Now there's another point that needs to be made besides the fact that the battery wears out, and that is that every battery has something called an internal resistance. In other words, you use up a little bit of the possible energy that the battery can produce just getting out of the battery, just getting out of the starting gate, so to speak. And that is because there's an internal resistance that must be overcome before you ever get to the resistors along the way in the circuit, be they light bulbs or buzzers or LED displays or even the wire itself. So sometimes we have to take into consideration the internal resistance, and sometimes we don't. Now, when we have a normal resistance, a load resistance, we use a capital letter R. When it's important to consider the internal resistance, we use the lowercase r. Now, imagine that we have a positive charge, a chunk of charge. And remember, the convention is to think about current as being the movement of this positive charge through a circuit, going from the positive part of the battery through the circuit and back into the negative part of the battery. That's the convention that we use. So the chunk of charge exits the positive post of the battery, fully revved up and full of energy. It goes through the wire, losing a negligible amount of energy, usually energy that we can ignore because it's so small, compared to the energy that will be used up doing work on whatever the resistor happens to be. And then finally, all that energy has to be used up when it comes back to the other end. It's kind of like thinking about water going over a cliff. And as the water falls over the cliff and goes down towards the bottom, maybe there's some water mills or turbine engines, turbine blades or something that will harness that falling water to do work. And so when the water finally gets to the bottom of the fall, then you've got a pump down there, this is where the battery comes in, to return the water back to the top of the cliff so it can fall over the cliff again and again and again. That's another good example of using water as an analogy. Of course, water evaporates and you don't have as much water each time you pump the electricity back to the water back to the top. So if we look at this equation right here, 18.1, the actual voltage, the useful or usable voltage that a battery produces, is the difference between the theoretical voltage, the voltage that's printed on the side of the battery, minus whatever voltage, and remember V equals IR, whatever Ohm's law, whatever voltage is used up just getting out of the battery. So this is the actual voltage, the actual work per charge that is available. Normally, we ignore this voltage loss due to internal resistance. One other thing about these batteries, they come in many different sizes. And you can have a 1.5 volt battery there, and a 1.5 volt battery there, 1.5 volt battery there. And these different 1.5 volt batteries, the reason they're different in size is because even though the voltage they produce is the same, the amount of current they produce is quite different. These bigger batteries, like here, are going to produce a lot more current than the smaller battery or these very, very thin wafer batteries. The voltage might be the same, but it's like having a lot of water going over a cliff and nearby just a trickle of water going over that same cliff. The voltage is the same, but the amount of current is different. So if we look at this drawing right here of a circuit, here's the positive post of my battery. By convention, when the current exits the battery, it has all the energy that the battery is capable of giving it. It travels through the wire because it wants to go downhill to the bottom, which is equivalent to the negative post of the battery. And as it goes downhill, it encounters a resistor, a load, something that it has to do work on. If it was water, we would say a turbine or a water mill, like a windmill. And then it uses up its energy and it comes back to the battery, where the battery gives it its oomph back again. And it does it over and over and over until the battery wears out. Now, by the way, notice these bands on the resistor. These bands are a color code that tells you, first of all, how many ohms of resistance this resistor has, and number two, its tolerance, its plus or minus, in terms of the precision of manufacturing and the accuracy of that ohmage that the resistor has been ranked for. And you're going to learn how to use this in a lab. So, all in all, we can say then that my total power, remember power is voltage times current. So we can say that the total power able to be delivered by the battery is going to equal the actual power that will be dissipated across the load and a little bit of residual power that is lost as a result of just getting out of the battery. So you can look at it that way as well. Normally, of course, your internal resistance is minuscule compared to the actual load resistance. If it's not, you start to have a whole lot of current going through that wire, and you could potentially have a short circuit. Now, resistors in series versus resistors in parallel. In this diagram right here, you have two light bulbs, and when the current exits and is pushed out of the battery, the current has no choice but to go through this light bulb number 1, and then go through this resistance, light bulb number 2, before it comes back to the negative post of the battery with 0 voltage, plumb tuckered out. Remember, my first 3 years of teaching were in the South, Chattanooga. Now, when this means that all the current has to go through each light bulb. There are no alternate pathways. This is what we mean by two light bulbs being in series. Very much like we talked about in chapter 16 when you had two capacitors in series. The current has no other place to go. So if I were to put an ammeter here, or an ammeter there, 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 it would give me the same reading all the way through. Exactly the same current. The electrical current cannot leak out of the wire. Every one of those readings would be exactly the same. However, if I had a voltmeter, and remember voltmeters have to be hooked up in parallel, so let's use a different color for a voltmeter. If I hooked up a voltmeter here in parallel across this wire, or more logically, I would hook up a voltmeter across this resistor and another voltmeter across this resistor to measure the amount of energy per charge I use up in resistor 1 and the amount of voltage or any energy per charge I use up in resistor 2, I would find that this voltage across resistor 1 plus this voltage across resistor 2 would almost equal the actual true voltage of my power supply, of my battery. There'd be a slight discrepancy if your instrumentation was sensitive enough to measure that internal resistance voltage loss. So as you go through the circuit, the voltage becomes less and less. The amount of current doesn't change. The speed of the current doesn't change. The speed of the current can't change because the battery here keeps pushing more and more current through the wire, just like if you turn a hose on, water keeps pushing the water that's up in front of it in the hose out the other end. It keeps on coming. Now, what if we wanted to replace both of these batteries with one single battery? I'm sorry, both of these resistors with one single resistor. How would we do that? Well, before I answer that question, I want to point out that when you see a configuration like this, a long line, which by convention is the positive post, and the shorter line, there's a shorter line, which is the negative post, that represents one electrochemical cell, one voltaic cell. It represents one, what is typically called in the United States, a battery with its little post. However, if I have a second battery, and you can put batteries in series or in parallel, if I had a second battery in series with the first, then I would have two long lines. Here's my first battery, there's my second battery, and that would look like this. Two batteries side by side like you would put in a flashlight. This, when you have them together, sorry about that. When you have them together like this technically in chemistry is called a battery. And each of these individual ones is called a cell or a dry cell. Of course, in the United States, we just call a single one of these a battery, and it's common language. So let's go back and answer the question, how do I find a single resistor that could replace two resistors that are in series? And in order to do that, we have to first of all remember that, and I'm going to be using the old-fashioned definition of the everyday definition of a battery. If this is my battery in my circuit, which gives me my total voltage, and we're ignoring any internal resistance voltage that would be dissipated, and we're ignoring any resistance in the wires. If this is my initial battery, I'm going to use up some of my energy per charge when I encounter the first resistor, and some in the second resistor, and some in the third resistor, and it goes on and on and on, depending upon how many resistors I have in series. This is only true for series in the circuit. Now, if I remember Ohm's law, V equals IR. So I come down here. So V equals IR, instead of having my total voltage, I can have my current times my total resistance. And keep in mind, the current doesn't change. So I don't need I1, I2, I3, and I total. The current is the same all the way through the circuit. It doesn't have any other place to go. So then instead of V1, I will say IR1. Instead of V2, I would say IR2. Instead of V3, I would use Ohm's law to say IR3. Now you'll notice that since the current is the same all the way through, you cancel out the current and you get this equation right there. So when resistors are in series, all you have to do is add up the resistors to get the total resistance. Piece of cake. POC. And once again, There we go. POC. Now you remember that capacitors are exactly the opposite. If you have capacitors in parallel and want to replace them with a single capacitor, then you add them up. So when capacitors are in parallel, you add the capacitance. When resistors are in series, you add the resistors. And as you might expect, it's just the opposite for when resistors are in parallel. So let's look at that. And by the way, here's a mercury switch, which we actually talked about when we looked at the thermostat right before Christmas. I'll let you do the problem itself because it's really quite a simple problem. So what about resistors in parallel? So when resistors are in parallel, a very important point, which is probably the most frequently forgotten rule, and that is that the potential difference across resistors that are in parallel is going to be the same. It's kind of like having a river going across the top of a tall mesa or plateau, and then it breaks up into several branches, and all the branches go over the same cliff, and then all the water flows back together again at the bottom into a single river. It doesn't matter which branch the water chooses to go over the cliff, all the water is falling through the same height. Every drop of water has the same potential energy. It's the same way with current going through multiple branches, as you will see in a minute. So, because of the law of conservation, if we look at, first of all, our picture here of two light bulbs in parallel, my electricity can either go this way and come back plumb-tuckered out, or, let's pick a different color again, my electricity could go this way and go through that light bulb and come back. It has two choices, to go through light bulb number 1 or to go through light bulb number 2. The light bulbs are in parallel. But in order to do so, that means that whatever my total current is, some of it goes there, the rest of it goes there. In other words, the current that goes through this branch, let's blow this up a little bit, the current which goes through this branch, which is I2, and the current which goes through this branch, which is I1, that the sum of these two currents must equal the total current. So if we back up here a little bit, this is what I just said. Every time the current encounters a branch in a circuit with parallel branches, it has to split up. Some of it has to go one way, some of it has to go the other way. Now in water, it likes to follow the path of least resistance, and the same is true in current. But you have to keep in mind that that doesn't mean that all the current takes the path of least resistance or goes through the light bulb with the least resistance. It means most of the current will go through the path of least resistance. Less current will go through the path that has greater resistance. So now when we come down here and say, what single resistor can I use to replace both of those resistors? And we're going to derive this equation now and show you where that came from. So if we come up to the top of the page, we just finished saying that your total current that exits your battery some of it has to go through branch 1, some has to go through branch 2, some has to go through branch 3. Depending on how many branches, it has to divvy itself up among all the branches. And of course, it's inversely proportional to the amount of resistance in each branch in terms of how much current goes through the branch. Not much resistance, more of the current proportionally will go through that branch. Now, because of Ohm's law, V equals IR, we know that I equals V over R. So let's substitute that in. So I'm going to have my voltage divided by my total resistance to substitute in for the total current. And remember, the voltage is the same. This voltage, change colors again, this voltage and this voltage and this voltage and this voltage are all the same. It's like all the different tributaries of water going over the same cliff and reconvening at the bottom. All the voltage drops have to be the same so that all the current from all the branches ends up back at the battery with 0 voltage. And so here we're going to have voltage divided by R1. This will be voltage divided by R2, voltage divided by R3. And since the voltage is the same, regardless of the branch, the voltage cancels. And you end up with this equation right here. One way of saying this is that the reciprocal of the sum, so this could be the sum right here, the equivalent or the sum, the reciprocal of the sum is the sum of the reciprocals. Now remember, for capacitors, it was capacitors in series where the reciprocal of the sum was the sum of the reciprocals. But with resistors, it's the reciprocal of the sum. It's the sum of the reciprocals when they are in parallel. And that's an important distinction that you do not want to forget. Now finally, a couple practical points. Household currents are always wired so that the electrical devices are connected in parallel. All the outlets in a given room are all in parallel. In case something goes bad in one outlet, the electricity can still go to the other outlets. Think of a Christmas tree light. If the lights are in series, if one light bulb goes out, the circuit is broken and all the light bulbs go out, and you have no idea, except through trial and error, which is the bad light bulb. But Christmas tree lights, at least in the more expensive and better light bulb, Christmas light packages, are wired in parallel. So if one light bulb goes out, the other light bulbs still work. And it would look something like this. If these are all the light bulbs, and this is the outlet right here that you plug into the wall, it kind of looks like this. And you got a little filament in there, or LED, and in there, and in there, and in there, and in there. And of course, if one of these light bulbs goes out, the electricity can just go right on past it both ways. You also have what are called circuit breakers. Almost all modern houses have circuit breakers, so that if for some reason too much current is trying to get through a circuit because you have too many things plugged in, especially things that demand a lot of current like space heaters, the circuit breaker flips off. And now no electricity goes through and won't go through until you unplug something and then flip that circuit breaker. And you're old enough, and you have been for some time, to know where the circuit breaker box in your house is, or at least you should find out. So in case you're home alone and for some reason a circuit breaker goes out, you can flip that switch back on again. It's very safe. The old-fashioned houses used to have a fuse, which was actually a little piece of metal that you could see through a little plastic window, and you had to screw it into your breaker box. Of course, it wasn't called a breaker box. It was called a fuse box. And if too much current tried to go through the circuit, it would go through that piece of metal and melt it. And that would break the circuit, and you'd have to unscrew the fuse, and then you'd have to buy a new fuse and screw it back in, assuming you unplugged a few things so the current demand wasn't as much. And of course, if you were rather poor or desperate and couldn't get to a store, you might, and this is extremely risky, you might take a coin like a penny and try to jam it in the place where the circuit, the fuse is supposed to be. And assuming you didn't get electrocuted, then the copper penny would bridge the gap and your electricity would be restored. Of course, now your wires are going to begin to overheat, assuming the copper doesn't melt, if you still have too many things plugged in. You're not going to see that issue too much anymore. You should also know this, practically speaking, every circuit in your house is either a 15 or 20 amp circuit. That's the limit. It will not allow you to have more current than that be demanded by things that you've plugged in. Finally, a three-way light bulb. A three-way light bulb allows you to choose between 75 watts, a brighter light bulb, 100 watts, or a really bright light of 175 watts, based upon whether one of these switches or the other of the two switches or both switches are closed or not. And so you might have in your house one of these kinds of switches where you turn the knob. There might be a little knob coming out right here, and you turn that knob and you have 3 different levels of brightness for that light bulb. That's how that works. And the last thing is, what if you have a complicated circuit like this with lots of different resistors? This is just like the problem on the chapter 16 test, where you had multiple capacitors, some in series, some in parallel, and you had to break it down till eventually you could replace it with a single capacitor. It's the same idea here. The first thing you want to do is look for resistors that are in series, because if the resistors are in series, all you got to do is add them up. And so here we have 8 plus 4, so I can replace these 2 resistors with a 12 ohm resistor, which is what they do there. Now over here, let's pick this color. On the right side, we have 2 resistors that are in parallel. The current some of the current's going to go there, some of the current is going to go there. Twice as much current is going to go this way, because you'll notice it's only a 3 ohm resistance compared to the 6 ohm resistor above it. So twice as much current will go this way, but then the current has to reconvene, come back together again on the other side. The voltage drop is going to be the same, because all the current enters this part of the circuit with the same amount of energy and must exit that part of the circuit with the same amount of energy, because they're falling over the same cliff, to use the water analogy. So we have to use the other rule that says the reciprocal of the sum. So if I want to find my equivalent resistance, EQ, the reciprocal of the sum is the sum of the reciprocals, 1 over 6 plus 1 over 3. Those are my 2 resistors. This is going to equal 1 over 6 plus 2 over 6, which is going to equal 3 over 6. That's 1 over R equivalent. So you take the reciprocal of both sides, and the R equivalent is 6 over 3, which is 2. And so we replace that with a 2 ohm resistor. And now you can see that these 2 resistors are both in series, which means we simply have to add them up. 12 plus 2, and we get 14 ohms resistance. That concludes lesson 1.